Today, we're diving into the story of a single, tiny subatomic particle. But this isn't just any particle. Oh no. This is the one that basically explains why you, me, and, well, everything we see exists at all. And in a pretty wild twist, it might also be telling us exactly how it's all going to end. So it all starts with a question that sounds almost childishly simple, right? Why do things have mass? I mean, why does a rock have weight, but a beam of light doesn't? It's something so fundamental to reality that we just take it for granted. But for physicists, this was a massive, gaping hole in our understanding of the universe. And believe me, the stakes could not be higher. You see, a universe without mass would just be chaos, a blurry soup of energy, with particles zipping around at the speed of light, never able to form anything. But in our universe, mass is like this cosmic glue. It gives matter substance, it allows gravity to grab hold and build everything from giant stars to, well, us. To figure this all out, we've got to look at our best rule book for reality, what's called the Standard Model of Particle Physics. Now, this thing is probably the most successful scientific theory ever devised, but for decades, it had this huge, universe-sized contradiction right at its heart. I mean, the Standard Model was just brilliant. It described all the particles we knew, it explained all the forces, but, and this is a huge but, it had one massive problem. The math. The beautiful equations that made it all work, they only balanced if all those fundamental particles were completely massless, which was a direct contradiction with, reality. We exist, we have mass. The theory was somehow both perfect and perfectly wrong at the same time. So to solve this paradox, a few physicists back in the 1960s came up with an idea that was just so elegant and honestly so strange, it completely changed how we see the universe. They proposed that mass isn't something particles inherently have, it's something they get. They imagined this invisible energy field filling every single nook and cranny of space, the Higgs field. The best way to think about it is like the whole universe is filled with invisible cosmic molasses. Some particles, like photons of light, just slice right through it, no resistance at all, so they stay massless. But other particles get bogged down, they drag, they interact with this field, and it's that resistance, that stickiness, that we actually perceive as mass. And this is the invisible, super high-energy world we're talking about. What you're seeing is a visualization of a particle collision. It's in these tiny, violent moments that the Higgs field is always there, always present, doing its job of giving substance to the universe. Now, here's a crucial distinction. If the Higgs field is like a giant ocean that fills all of space, the Higgs boson is like a wave on that ocean. It's a tiny ripple, a real physical particle that you could actually find. So finding this boson wouldn't just be about finding a new particle. No, it would be the smoking gun, the absolute proof that the entire field, the entire mechanism for mass, was real. And just like that, one of the greatest scientific hunts in human history was on. For almost 50 years, thousands of scientists from all over the world dedicated their entire careers to one single goal: finding that ripple. The theory was dreamed up way back in 1964, but look at this timeline. The final proof didn't come until 2012. Think about that. An entire generation of physicists lived and worked between the idea and the confirmation. It was a true marathon of human curiosity and just sheer persistence. And this hunt required building the largest, most complex machine humanity has ever created, the Large Hadron Collider at CERN. It's this 27-kilometer ring buried deep underground on the border of France and Switzerland, and its whole job is to smash protons together at nearly the speed of light just to recreate the conditions of the Big Bang for a fleeting fraction of a second. So after sifting through data from trillions, that's trillions with a T of collisions, they found it. Now, these graphs here, they show the results from two totally independent teams. You don't have to worry about the details, just look for that little bump in the data on each chart. That tiny little spike, that small excess of events showing up in the exact same spot for both teams, that was it. That was the signal they'd been looking for 50 years. That's the Higgs boson. That's how you know it's real. Okay, so finding the Higgs completed the Standard Model. It was a monumental, unbelievable triumph. But the story doesn't stop there. Not even close. In fact, by finally measuring the properties of this particle, we opened up a totally new chapter, one with some pretty staggering implications for the past and the future of our entire cosmos. So get this, some theories suggest that right after the Big Bang, the universe was so dense it was teetering on the edge of just collapsing back in on itself, into a black hole. The Higgs field, by snapping into existence, might have provided just enough of an outward push to stabilize spacetime, allowing the universe to expand and form. So it didn't just give us mass, it might have literally saved existence itself. So when scientists finally pinned down the Higgs's mass, it came in at about 125 giga-electron volts. Now this wasn't just some random number. It turned out to be a terrifyingly specific one, because according to all our calculations, this exact value puts our entire universe in a very strange, very precarious state.
As theorists at Harvard put it, this discovery hints that, and I'm quoting here, the cosmos may be destroyed by the explosion of a negative energy bubble. Yeah, that sounds like something straight out of science fiction, but it's a real possibility that comes directly from the measured mass of the Higgs.
The technical term for this is metastable. It means our universe isn't truly fundamentally stable. It's more like a pencil balanced perfectly on its pointy tip. It's fine for now, but the tiniest nudge could make it fall. In the universe's case, a random quantum fluctuation somewhere, maybe trillions of years from now, could trigger a chain reaction. It would create a bubble of a new, more stable universe that would expand at the speed of light, rewriting the laws of physics and just erasing everything in its path. So this incredible discovery, it answered a 50-year-old question. But in doing so, it also threw open the door to even bigger mysteries. It made us realize just how little we really, truly understand. You see, the Higgs completed the standard model, but the model itself is incomplete. It says absolutely nothing about gravity, the most familiar force of all. It has no particle to explain dark matter, that invisible stuff that's holding entire galaxies together. And it has zero answers for dark energy, the mysterious force that's pushing the whole cosmos apart. I mean, to really put it all in perspective, just look at this chart. The entire standard model, every particle we've ever found, every force, including the Higgs boson, it only describes that tiny 4% sliver of visible matter. 96% of reality is still a complete and utter mystery to us. So, in the end, the Higgs boson wasn't the final answer. It was the beautiful, satisfying end of a chapter. It proved our theories about the visible universe were spot on, and by doing that, it gave us the tools, and maybe more importantly, the confidence, to start tackling the enormous 96% we still can't explain. The whole journey to find the Higgs started with a simple question about mass, and it ended with these profound, almost frightening questions about the nature of reality and our ultimate fate. It took 50 years and the biggest machine on Earth to complete one theory. So the question now is, what's it going to take to finally complete the whole picture?